from making eerie fog to broiling cauldrons that are cold to shipping protein samples across the country. Dry ice is, well, sublime. So dry ice is frozen or solid CO2, so carbon dioxide. And what happens is that it has this ability to do this thing called sublimation. So we call it dry ice because it skips over the wet part. It's really, really hard to get liquid CO2. That's why smoke, fire putter outers, fire extinguishers, they have to be really, really high pressure because those have liquid CO2. But CO2 really likes to be a gas. And it will be a solid if it doesn't have enough energy to be a gas. So if it's really, really cold, like under 80 degrees, minus 80 that is, it's gonna be a solid. And that's where we get dry ice. But then you see that this dry ice starts like evaporating. And so it's going straight from the solid to the gas state because the CO2 molecules really don't like each other that much. So unlike water molecules, say, where the water molecules are really sticky for one another, they have this thing, what we call polarity, where basically so H2O, two hydrogens and an oxygen, those are linked up by sharing negatively charged subatomic particles, basically these negatively charged things called electrons. And what's important to know is that the oxygen is going to hog those electrons away from the hydrogens. And the other important thing is that you kind of have this triangle, this like Mickey Mouse situation going on. So this is going to make it so that one side is kind of going to be positively charged and one side is going to be negatively charged. Opposite charges attract, and so the water molecules stick to one another a lot. With CO2, what you have is you have a carbon and two oxygens, and the carbon's stuck in the middle, and what you have is you actually have them in a line. The oxygens are going to be pulling the electrons away from the carbon, but they're going to be canceling each other out, and so overall the molecule is just like blah, like no charge, and so it's what we call non-polar. This makes it so that the carbons don't really like each other that much. They don't have those like partial positive, partial negative parts that can really stick together, and so this is going to, if they have enough energy, allow them to get like apart from one another and just move around randomly. That is, be like a gas, just like float around. But you need energy to be a gas, because even though they don't like each other that much, they still need energy to break away from interactions with one another, and they need energy to like move. And so energy, when we think about energy, we think about heat. So heat is a measure of like the average kinetic energy, so the average movement of the particles. And so the more heat you have, the more energy those particles have. And different molecules will have different amounts of heat that they need in order to be in various phases. But it's not just heat that you need. You also need to be able to overcome the pressures that are put upon you. So if you think about if you have CO2 and you drop it in water, well, now what's going to happen is that the CO2 has all this water around it. And so it has to overcome the pressure of the water coming down on it in order to escape and become a gas, even if it has enough heat to have been like a gas if it was just like on the surface of the water. Well, if it's on the bottom, well, it's got all that extra water weight on top. So what happens is that these CO2 molecules, as they sublime, so as they go from being a solid to being a gas, when they're trapped inside of the water molecules the CO2 molecules kind of like gang up and they form these bubbles. And these bubbles are then going to rise to the surface, because what happens is inside these bubbles, the CO2 molecules are all banging around trying to get out. Well, they're not really trying to get out, but they're like banging against the walls because they're moving around randomly. They've got this energy. They're not like hooked up to one another anymore. They can like move around, but they're moving around. They're kind of like going in all directions. And so this like cancels out. That's why you get this like bubble shape. But what's going to happen is there's less pressure on top because there's less water weight on top. And so these bubbles are going to rise to the surface. When they get to the surface, they're going to pop, because what's going to happen is that they were surrounded by this like shell of water, where these water molecules are kind of like all hanging out together. And then when you get to the surface, well, now it's like you can't have a bubble made of just water. That's kind of like making a bubble made of cement. It's just not going to work. There's not enough, there's too much surface tension. So these water molecules like hanging out with one another, they're really strongly sticking to one another, and so you get this like surface tension, and you can't like expand like you would do like with a balloon. It's more like cement. And so these bubbles are then, when there's not the water weight on top and they're all pushing out, and then boom, they're gonna pop. So what's going to happen now, though, is that if you were to add soap, well, now what's going to happen is that instead of being surrounded by just like a shell of water, you're surrounded by this kind of like bi-layer membrane with a little bit of water in between. So soap is what we call a surfactant. So it's a surface acting agent. It lowers the surface tension. You can think of it kind of like sneaking in between the different water molecules, breaking up those networks and making it easier for your bubble to expand. Also, what it does is, because soap is what we call amphiphilic, it has this part that is hydrophilic or water loved, and this part that is hydrophobic or water avoided. Now, if you put something like that in the presence of, say, like air, it's going to form this like bilayer where the hydrophobic parts are going to be sticking out and the hydrophilic parts are going to be sticking inside, and then inside of between those there's going to be like a sandwich of water, and so this is going to help it form this like layered membrane, and now this bubble can expand. But as it starts expanding, then it gets too big, and eventually, even though you have that surfactant, the water molecule is just not, there's just too much pressure banging out, and so you get it to pop. But until then, you can allow these bubbles to kind of like hang around for a while, and this is why you can get this like bubbling cauldron look. So when you dump CO2 in water, what's going to happen is not only do you see bubbles, but especially when those bubbles get to the surface, you're actually going to see fog. And when we talk about fog, we're seeing liquid water that's in the air. And the way that we get this liquid water there is that it's kind of like hitching a ride with the CO2. So as those CO2 bubbles are rising to the surface, they're making this interface that it's easier for water to get into the gas phase, because there's less pressure coming in there than there would be from like all this other water around it, and so it can kind of like sneak into that. So the reason, like, so you see like water molecules are able to evaporate more easily from a surface because there's less pressure. They're also able to kind of sneak into that bubble, and so they can sneak into that bubble, but they can't stay, because they're sticky for one another. They need more energy to overcome one another, and so what happens is that they can't stay in that gas phase, especially once you get to the surface, and so they're actually going to condense. They're going to turn into a liquid. They're not going to go back to being a solid. Well, the water wasn't a solid to begin with, but basically when you have a liquid, the molecules can slide around from one another, so they have more freedom than they would in a solid, but they don't have enough freedom to like truly break free from one another. They don't have like enough energy to truly break free from one another, and water needs more energy than CO2 needs for that, because the water molecules have that stickiness to one another. So what's going to happen is that because inside of this bubble it's not hot enough for the water to stay apart from one another, the water molecules are going to condense, and so they're going to form this liquid water, and this is what you're going to see as fog. So we can get this fog effect based on just like dropping CO2 into water. A thing that we should mention, though, is that CO2 is going to be really, really, really cold, which is what makes it great for doing things like shipping proteins across the country, because it's going to keep those proteins around minus 80 degrees Celsius, so about what we put in one of those big minus 80 freezers, because that's around the temperature at which CO2 sublimes. So when it goes from a solid to a gas, and so we have to keep it in like styrofoam and in like big insulated containers in order to keep it from subliming, but it's still going to sublime, so it's not like you can just stick a little bit of CO2 in here and come back 10 years later and it'll still be there, but it'll give you a few days worth of coldness so you can ship your samples. But it also means that you need to be really careful when you're working with it, so like wear your safety goggles, wear your gloves, your little like freezer gloves, because you don't want to get dry ice burn, which can hurt really, really bad. So cold burns are nothing to joke about or laugh about or minimize. Cold burns are totally serious, so be really careful when you're working with dry ice. Yeah, so CO2, we get the bubbles, we get the water condensing in those bubbles as the CO2 tries to escape. The water can't make it all the way, it tries. So it condenses, it goes back to being a liquid. You get that fog effect. If you add soap, you can get those CO2 bubbles that are trying to escape to actually stick around a while, because that soap is going to kind of loosen up the shell around the bubble, making it so that the bubble can like expand and things, and it can stick around rather than just collapse right in, because water is going to try to cinch in on itself and cinch in on all that stuff that's inside of it, making your bubble burst. And so you can get the bubbles to stay around a little with soap, and then you get your cool cauldron effect. So hope that helped you understand some of the coolness about CO2, and hope you have a good Halloween if you're watching this on Halloween.